Hello everyone, I'm Sunanta from SNS College of Technology, Department of Mathematics. As the continuation of the lecture series in diagonalization, we are going to see reduction of quadratic form to canonical form in this lecture video. So this presentation explores the process of simplifying quadratic form into canonical form. That is, quadratic form is an equation form and canonical form is a matrix form. So highlighting its significance across various scientific and engineering disciplines. So now let us see what is quadratic form. So quadratic form is a homogeneous polynomial of degree 2 in n variables, commonly expressed as q of x is equal to x transpose ax, where A is a symmetric matrix. These forms are fundamental in linear algebra, representing various geometric entries such as conic sections and quadratic surfaces. They also describe energy functions in physics and objective functions in optimization problems. So here this is an example of quadratic form. So common example is ax square plus 2bxy plus cy square, which defines the conic sections like ellipse, parabolas and hyperbolas. Now let us see canonical form of a quadratic form. So diagonal form, the canonical form is a simplified diagonal representation. Q of y is equal to lambda y1 square plus lambda 2 y2 square plus etc. up to lambda n yn square. Next is variable change. So this form is achieved through a linear change of variables y equal to p inverse x, where p is an invertible matrix. Next is simplified analysis. The canonical form generally simplifies the analysis and classification of quadratic form, making their geometric properties more evident. Next is method of reduction. So that is, the process is called diagonalization. Here let us see. This method relies on the orthogonal diagonalization of a symmetric matrix A associated with the quadratic form. So the eigenvalues lambda I. So here if we take 2 by 2 matrix, we will have lambda 1 and lambda 2. If we take 3 by 3 matrix, we will have lambda 1, lambda 2 and lambda 3. Of a matrix A forms the diagonal entries of the canonical matrix A, where the corresponding eigenvectors form the columns of the transformation matrix P. So the quadratic form transforms Q of x equal to x transpose AX into y transpose AY, where A is the diagonal matrix of eigenvalues. So this method preserves crucial properties like definiteness and rank of the quadratic form. Next is Lagrange's method of reduction. First is completion of squares. So this method involves a stepwise process of completing the squares to eliminate cross product terms from the quadratic form. Next is sum of square forms. So it directly converts q of x into a sum of squared terms, bypassing the need for eigenvalue decomposition. Next is manual calculation. Lagrange's method is particularly useful for manual calculations and when dealing with symbolic forms of quadratic equations. So next is example, reduction of a binary quadratic form. So here the given form is q of x comma y is equal to 3x square plus 4xy plus y square. So the matrix form of this will be 3. So we are going to divide this 4 by 2. So we have 2, 2 and 1. So the eigenvalues of this particular matrix is 4.561 and minus 0.561. So since the one eigenvalue is positive and the another one is negative, we call the nature to be indefinite. Next, canonical form will be lambda y1 square plus lambda y2 square. So we have 4.561 y1 square minus 0.561 y2 square. Next is transformation. So transformation matrix P is formed by eigenvectors of A. The example demonstration will be followed. Next is summary. Simplification. So reduction simplifies complex quadratic form to a canonical diagonal form, making them easier to analyze. Next is classification. This enables clear classification and more efficient computation in various contexts. Next is diverse applications. So applied in optimization. Example, constrained optimization in physics and in statistics also this method is used. Next is key tools. Primary methods include orthogonal, diagonalization and Lagrange's method supported by Sylvester's law of inertia. Thank you.